The last thing that we talked about in this class before we took off for our field trip at West Edmonton Mall 2 days ago was vertical circular motion. What do we do when an object is going in uniform circular motion, but not in a nice horizontal, easy circle, but rather it's going in an upside down loop, like the roller coaster did at the West Edmonton Mall? Well, we analyzed two situations there. One, the roller coaster car was upside down at the top of the loop, and two, the roller coaster was right side up at the bottom of the loop. We could analyze anywhere in between, but it would become a two-dimensional problem if we did. Wouldn't be crazy difficult because we've dealt with two-dimensional problems before. It's just vector analysis, right? But we don't need to do those points in between because the two extremes are the top and the bottom. Let's focus on the two extremes. Okay, when you experience the most g-force and when you experience the least g-force. In both of these cases, we have two forces acting on the roller coaster car, or it could be the keys on the end of my string, or it could be anything revolving in a vertical circle. Two forces acting. One force is force of gravity, and it's going to act down in both cases. Force of gravity always acts down, right? What's the other force that acts on this car, both at the top and the bottom? The normal force, good. Which way does the normal force act on the car or the keys or whatever it is when you're at the top of the circle, Lewis? It acts downward, good. And Carrie, which way does the normal force act when you're at the bottom of the circle? It acts upward. Imagine if you're at the bottom of the circle and both of those forces were acting downward, you wouldn't stay in a circle, right? You'd end up going downwards, the direction of both of those forces. All right, these are both free body diagrams. We know from our last unit, whenever we see a free body diagram, we always go to that next step. F net is equal to all of those forces added together. So in this case, Fg plus Fn. And in this case, it'll also be Fg plus Fm. The net force used to be for us m times a. Well, it still is, kind of. But m times a now is m times the centripetal acceleration, because that's where it's really accelerating, right, is going around a circle, accelerating toward the center of the circle. So instead of saying m times a for F net, we're going to say what? Yep. Good. It's still really m times a, right? But it's a very specific m times a. M times the centripetal a, centripetal acceleration, is equal to Fg, which is really just m times g, plus the normal force. Okay, again, in both cases. At this point, we're probably going to have some numbers in the question, right? At this point, we're going to plug those numbers in. We don't worry about signs, positives or negatives, until we go to plug the numbers in. But this is the point where we're going to plug the numbers in. So this is the point where we have to start worrying about positives and negatives. Let's say we're at the top of the circle there, diagram number 1. Which way does gravity act when you're at the top of the circle? Yep. It acts downward. So we're going to make it a negative value, right? Don't put in the negative just for Fg. Put in the negative if you put in a value for Fg. Okay, what about the normal force? Which way is it acting when you're at the top of the circle there? Seth? Yep. It's acting downward as well. Good. So that's going to be a negative value of force as well, because it's acting downwards. But what about the centripetal force, which is really the net force, right? The total force. You get two downward forces. The net force is going to act which way? Got it? Downwards as well. Look at the diagram. If you're at the top of the circle, the centripetal force always points toward the center. Where is the center relative to you? Down. So the centripetal force will be downward. We'll make it a negative value. At the top of the circle, all three of them are going to be negative values. That's actually, usually we don't like negatives, right? But if they're all negative, it actually makes life easier for us. So in this case, not too bad. What about the bottom of the circle? At the bottom of the circle, you're going to plug numbers in. Fg will be what? Yep. It's negative because it's acting downwards, right? What about, this should be Fn, right? Tony, what about Fn? Which way is Fn acting at the bottom of the circle? Upwards. So it's going to be what? Negative or positive? We're going to make that one positive. Again, we're not going to worry about that until we plug numbers in. Okay, but once we start plugging numbers in, we got to start worrying about negatives and positives. This is the tough one right here, mv squared over r. At the top, it was easy because they're both acting downward. The net force has to be downward. But here we've got a force acting downward and a force acting upward. Which way is the net force? The centripetal force. Always when you're at the bottom of the circle. Yep, see? It's upwards, yeah. You're at the bottom of the circle. The center of the circle is above you, so the centripetal force has to act upward. It's going to be a positive value. If it wasn't positive, then it wouldn't be a centripetal force. Because if the net force wasn't toward the center, it wouldn't be going in a circle. And if it wasn't going in the circle, there wouldn't be a centripetal force. So at the bottom of the circle, it has to be positive, negative, and positive. All right, plug numbers in, solve for whatever you're looking for. Got it? We worked on some questions on Monday before we went on our field trip on this vertical circular motion stuff. Is there any issues with those questions? The upside down circles. All we're looking for in those questions is solving for Fn or solving for speed or solving for R or something. But they're all, every single one of them, they all use this, either this or this. And we just have to plug in the signs. Yeah, Luce? Yep. All right, guys, we got a request to go over number 3 here, so let's take a look at that. There's a 0.98 kilogram rock is attached to a 0.40 meter rope and spun in a vertical circle. The tension on the rope at the top of it is 79 newtons down. What's the speed of the rock at that point? So where are we analyzing here? We're in a vertical circle. Where are we analyzing this rock, top or bottom? At the top of the circle, right? That's an easy question. Where are we analyzing it? Top of the circle. There's the rock. Now, there's 2 forces acting on that rock. One's the force of gravity, and it acts down. I'll give you that one because that's the easy one. The other one is what? Yep. Let's call it the normal force. You could call it Ft for the force of tension in the rope that's holding this rock in place. Or, you know what? Let's just call it normal force so that we're consistent for every one of these questions. By the way, if you called it Ft on your test, I wouldn't mark that wrong. Or FQ or FS or whatever you want. I wouldn't mark it wrong. All right. What do we do at this point? Same thing as we always do when we have a free body diagram. Zach, what is that? What's the next step? Good. F net is equal to the sum of those forces, Fg plus Fn. F net is, Bart, what's next here? F net is also equal to what? Mass times acceleration, good. But acceleration in this case is centripetal acceleration, so it's going to be v squared over r, right? So it becomes, instead of m times a, it becomes m times v squared over r. So you're right, Bart, when you say m times a, but this is the a this time. The force of gravity plus the normal force. What are we looking for here? The speed of the rock. We're looking for v. Notice I haven't plugged any negative signs in yet. Why haven't I done that? Why haven't I worried about positive and negative yet? Yep. I haven't put any numbers in yet. Good. Okay, let's start putting some numbers in. When I do that, I'm going to have to start worrying about positives and negatives here. Do we know the mass? We do. 0.98 kilograms. We don't know what V is. That's what we're trying to find. R is 0.40. If the length of the rope is 0.40, then that's going to be the radius of the circle. Fg is the force of gravity, 0.98 times 9.81. And Fn says the tension in the rope is 79 newtons. That's the normal force. Positives and negatives. Gravity is going to be positive or negative? Negative, always, right, Seth? Always negative, because it's pointing downwards. The tension in the rope, or the normal force, is going to be which way? Allie, which way is the tension in the rope going to be, the normal force? Up. Take a look at the diagram there. Yeah, the normal force is going to act down when you're at the top of the circle, right? Jordan, which way does the centripetal force act when you're at the top? It's negative because it's acting downward. Now notice I haven't plugged in all my numbers for mv squared over r, but I plugged in some of them, right? So I'm going to put my sign in there now, right? Right, Alana? So now we solve for v. Let's pull up the calculator here. Let's get the right-hand side first. We're going to say negative 0.98 times 9.81. Okay, negative 9.6. Let's subtract from that 79 newtons. Negative 88. Okay, let's take the 0.4 over to the other side by multiplying. Let's Let's take the 0.98 over to the other side by dividing, except it's a negative 0.98. And then let's square root that. When we do, we get 6.0 meters per second. So we'll say V 6.0 meters per second. If it was going faster than this, you can imagine that the tension in the rope would have to be greater because the rope has to pull stronger in order to hold it in the circle, right? If it's going slower, then you'd find the tension in the rope would be smaller. Wouldn't have to pull as hard to hold it in place. Does that make sense? Who asked me for number 3? Is that okay? The last thing that we talked about on Monday before we left, we didn't have a chance to go over any problems with this, but we experienced this yesterday as you were working on the assignment booklet for your field trip. Minimum speed. You guys know, I demonstrated this for you with the set of keys on Monday. If you swing your keys really, really fast, they go in a vertical circle, no problem, right? If you slow them down and slow them down and slow them down even more, you find at some point they no longer go in a circle. There is a minimum speed of those keys or of the roller coaster or of whatever it is that's going in the vertical circle, that thing has to be moving in order to stay in the circle. Below that speed, it falls out of the circle and it's not circular motion. Above that speed, it stays in the circle. In order to find that minimum speed, we talked about this again on Monday, but just go through it real quickly again. To find that minimum speed, we got to draw a free body diagram, but we got to draw the diagram of the object at the top of the circle. The minimum speed has no bearing on the bottom of the circle. You can be going as slow as you want and still stay in the circle when you're at the bottom. So we're going to analyze the top of the circle. There's FG at the top of the circle acting downward. There's Fn at the top of the circle acting downward. There's FG, let's say F net is equal to Fg plus Fn. But when you're solving for minimum speed, this only happens when you're solving for minimum speed. Fn is 0. Swing those keys around my head. I can't do it today because I forgot my keys at home, but swing those keys around my head. As I slow down, I slow down, I slow down, you notice the string holding the keys in place, okay, that was joining my hand to the keys, had no tension in it. Okay, at the minimum speed, the string didn't have to pull. When the roller coaster's going around the track, if it's going at just the minimum speed necessary to go around the vertical circle, then the track doesn't have to push on it. Gravity takes care of all the work. So at that point, we'd say Fn is equal to 0. Then we'd say mv squared over r is equal to m times g. Okay, mg, the force of gravity. We'd cancel out the m. And we'd be left with v is equal to v squared over r is equal to g. And typically at that point, we're solving for minimum speed. We'd rearrange this equation to solve for v. All right? Okay, let's do a problem where we have to actually find the minimum speed. 5.6 on 262. This is a new one for you. This is a 700 kilogram roller coaster car full of people, goes around a vertical loop that has a diameter of 50 meters. What's the minimum speed that it has to be going to stay on the track? So if it's going to fall out of the loop, where's it going to fall out of the loop? Lana, if it's going to fall out, where's it going to be? At bottom or top? The top. So let's draw a free body diagram at the top of the circle. There's the roller coaster, top of the circle. Bart, there's two forces acting at the top of the circle usually. What are those? What's one of those two forces? Gravity, and it acts downwards, right? Good. Caitlin, what's the other force that acts when you're at the top of the circle? Good. And which way does it act? Good. The normal force acts downward. So at this point, we probably say what next? Jacob, what's next? Yeah, this question is the same as any other question to this point, right? F net is equal to the sum of the forces. Okay, net force is mv squared over r. Oh, wait, there's a shortcut here. What can I do? Yep. Okay, before I cancel out the masses, oh, I gave it away because I thought you were going to give me the right answer there. Yeah. I get rid of Fn. Why do I get rid of Fn? Because above the minimum speed, the track has to help gravity. Below the minimum speed, well, it's not going to go in a circle. at the minimum speed, gravity supplies all of the centripetal force. The track doesn't have to help. So we're going to just get rid of it. Fg, by the way, is m times g. Now, Jacob said we could cancel out the masses. We can now because it appears in every term. Because v squared over r equals g. Solving for v, r is 50 meters. No, r is 25 meters because that was the diameter. G is 9.81. Now, technically, that's a negative because it's downwards, and that's a negative because it's downward. Although they cancel each other out, so if you left them both as positive, it would work. Let's solve this one now. Let's say 25 times 9.81. It's actually negative 245, right? Let's just cancel the negatives off right off the top. Let's square root that. We're going to end up getting 15.7. 15.7 meters per second. So, thank you, Barb. So if you're going 15.7 or 15.8 meters per second, you might be a little scared on this roller coaster because you're barely going fast enough to make it around the circle. But you'll make it around. If you're going 15.6, what's going to happen? Well, you're almost going to make it around, but not quite. So what's going to happen to the roller coaster when it gets to the top? It's not going to fall straight down, but it's not going to stay on the track. It's going to kind of go like this. Going around, going around, going around, going around, and that's not so good. That would be a projectile motion problem now, right? As opposed to a circular motion problem, because it's not the track pushing on it, it's just gravity and inertia right now. All right? There's at least once on your assignment that you have to do this. I can't remember if it's just once or more than once, but at least once on your field trip assignment where you have to find that minimum speed of the roller coaster. Yep. Would we have to do a question like this with projectile motion? No, you won't. But boy, wouldn't that be a good question? Or I wonder if I could somehow integrate that into the incline plane / pulley / friction / elevator / projectile motion problem. I wonder if I could integrate that somehow. I'm not sure. But no, you wouldn't have to do it circular motion and projectile motion at one time. It'd be a good question, but it'd be a hard question. A little bit beyond where you guys are right now. Okay, let's see what we can do with these two questions. This will prepare you well for one of the questions on your assignment. We'll take a look at these in a few moments once you've had a chance to work on them, and then we'll go from there. Let's take a look at number 2 here. 2 is a little bit different. We're asked for a maximum radius that the loop can be if the car with a speed of 20 meters per second is going to go around it safely. Maximum radius. Well, maximum radius kind of corresponds to a minimum speed, right? Because in the end here, if I have a certain radius of a loop and I spin these around at a certain speed, or spin the roller coaster around at a certain speed, and I go below that speed, then it's going to fall out. But if I keep the same speed and I increase the circle, well, then it's got to go faster to go around the loop, right? So it's kind of the same thing. You want to find a maximum radius. It's like finding a minimum speed, except you're solving for r instead of v. You're still going to set Fn equal to 0. So it's going to look like this, Bart. Here's the roller coaster at the top. You get Fg acting down. You get the normal force acting down. We're going to say F net is equal to Fn plus Fg, but we're going to cancel out, not cancel, but we're going to get rid of Fn, because again, it's the same thing. Be above a certain radius, then it's going to fall out of the loop. What's the maximum radius? Well, it's the point at which the track doesn't have to push down. So we're going to say F net is equal to Fg, where mv squared over r will be equal to m times g. But this time, instead of solving for v, we're going to solve for r. Masses cancel, by the way. V is 20 meters per second. G is 9.81. Technically, we should put in negatives for both of those because they're both acting downwards. The r goes up by multiplying. It becomes 20 squared, by the way, is 400. And then we're going to take the neg 9.81 over by dividing. So 400 divided by 9.81 gives me an r of 40.8 meters. That make sense? So if you're going that speed, you can keep increasing the radius of the circle to a really, really big radius, almost half a football field length. In other words, your loop can be almost the full length of a football field before it ends up falling out. Okay? You guys okay with this? Yeah, Carrie? Yeah. Yes, if you increase your radius beyond 40.88 meters, that doesn't mean you're going to fall out if you increase your speed. But at that speed, that's the biggest radius you can have. The question could be phrased differently. Here's the radius. What's the minimum speed that you can go? You'd solve for that, and it would have worked out to be 20 meters per second, right? So anything above that radius is going to fall out. Anything below that speed, it's going to fall out. Yep. No, it is upside down. But question number one, neglecting friction, that's not what that's inferring there. It just means, look, we get gravity in the normal force. Don't worry about the force of friction mixed in there as well. There truly is a force of friction in there, but it's minimal. You saw the way, 2 days ago, you saw the way the roller coaster rode on the tracks, right? There's friction there, but there's not a great deal of friction between the roller coaster and the track. So they're just saying, don't pay any attention to friction, which is good because you don't know how to deal with friction in these questions anyways. Okay? So if I left that off, you'd solve the problem the exact same way. All right?